2,000 characters, 15 columns of text, a previously unknown philosophical work that has been unread for nearly 2,000 years. In February 2024, 3 young researchers announced they had done what scientists said was impossible. They used artificial intelligence to read the inside of a sealed ancient scroll without ever touching it. The scroll was carbonized by the eruption of Mount Vesuvius in 79 CE, the same eruption that destroyed Pompeii. The scroll had been buried under 65 feet of volcanic rock for nearly 2 millennia. When it was excavated, it was nothing but a charred cylinder of carbon that crumbled at the slightest touch. For 275 years, no one could read it. The ink was made of carbon. The papyrus had turned to carbon. It was black on black, invisible. Every attempt to physically unroll these scrolls destroyed them. Between 600 and 800 scrolls like this one sit in museum collections around the world. They represent the only intact library to survive from the ancient Greco-Roman world. And until now, their contents were locked away forever. Then a computer scientist, a former tech CEO, and 2,700 volunteers from around the world launched something called the Vesuvius Challenge. They fired X-rays through the sealed scrolls. They trained machine learning algorithms to detect patterns no human eye could see. And they offered $700,000 to anyone who could read 4 passages of 140 characters each. The winners read over 2,000 characters. They revealed a text discussing the nature of pleasure written by an Epicurean philosopher named Philodemus. Words that no human being has read since the Roman Empire. This is the story of how artificial intelligence unlocked the secrets of the ancient world. The eruption. On August 24th, 79 CE, Mount Vesuvius erupted. Most people know about Pompeii, but there was another city even closer to the volcano, Herculaneum, a wealthy resort town where elite Romans built seaside villas. Herculaneum was buried under approximately 20 meters of volcanic material. That is 65 feet of superheated gas, ash, and rock. The pyroclastic flows reached temperatures between 300 and 400 degrees Celsius, hot enough to kill every living thing instantly. But something strange happened. The extreme heat carbonized organic materials rather than burning them to ash. Wood turned to carbon, food turned to carbon, and papyrus scrolls turned to carbon. Then the volcanic debris sealed everything in an oxygen-free environment. Without oxygen, there was no further decay. The scrolls were preserved in their carbonized state for nearly 2,000 years. As one scholar explained, the heat of the pyroclastic flow, while instantly fatal to any living being, was just right to carbonize these papyri instead of merely setting them alight. The Villa of the Papyri. In 1750, workers digging a well near the buried city struck ancient structures. They had discovered a magnificent Roman villa that would become known as the Villa of the Papyri. The villa was enormous, over 200 meters of frontage, a water feature longer than a modern Olympic swimming pool, and over 90 bronze and marble sculptures. It was so impressive that oil magnate J. Paul Getty replicated it in Malibu, California. That replica is now the Getty Villa Museum. The likely owner was Lucius Calpurnius Piso Caesoninus. He was Julius Caesar's father-in-law, one of the most powerful men in Rome. Between 1752 and 1754, excavators discovered the villa's library. They found approximately 1,800 full and partial scrolls, perhaps 1,000 original volumes. At first, the excavators thought they had found logs or carbonized fishing nets. Then they realized what they were looking at: the only intact library from the classical world. The only one. Every other ancient library was destroyed. The Library of Alexandria, the libraries of Rome, all gone. But this one survived, because a volcano buried it under 65 feet of rock. The impossible problem. The scrolls emerged from excavation as blackened cylinders, tubes of charcoal, extremely brittle. They crumbled at the slightest touch. Early attempts to read them were catastrophic. In the 1750s, an artist named Camillo Paderni tried slicing scrolls in half, copying any visible text, then scraping away layers one at a time. This destroyed hundreds of scrolls. In 1756, a Vatican conservator named Antonio Piaggio invented a mechanical unrolling device. It used weights and threads to slowly unwrap scrolls millimeters at a time. The first scroll took 4 years to unroll. The process still damaged many scrolls, but it revealed some text. By 1800, only 18 of approximately 1,800 manuscripts had been unrolled. The extreme difficulty and risk made progress agonizingly slow. Various mechanical and chemical methods were tried over the following 2 centuries. All caused significant damage or destruction. By the late 20th century, scholars faced an impossible choice. They could try to physically open the scrolls and probably destroy them, or they could leave them sealed forever, preserving them but never reading their contents. Between 500 and 800 carbonized scrolls remained unopened. Their contents were a tantalizing mystery, and there was an additional problem that made everything worse: the ink. Ancient scribes wrote on papyrus using carbon-based ink made from soot or charcoal mixed with gum arabic. When the scrolls carbonized, the carbon ink became virtually indistinguishable from the carbonized papyrus. Carbon on carbon, black on black. Even if you could somehow see inside a sealed scroll, you would see nothing but blackness. The computer scientist. In 1995, a computer scientist at the University of Kentucky named Brent Seals began working on a different approach. His insight was simple but revolutionary. The goal should not be to physically unroll the scrolls. The goal should be to virtually unroll them. Use X-ray CT scanning to see inside the rolled structure. Then use computational methods to digitally unwrap the layers. Flatten them into readable images without ever touching the fragile papyrus. Seals spent decades developing the technology. In 2015, he proved the concept on a different ancient scroll, the Engedi scroll from Israel, a badly charred Hebrew manuscript that had been stored unopened for over 40 years. Seals scanned it, applied his virtual unwrapping software, and successfully read 35 lines of text. The scroll contained chapters from Leviticus. It was the oldest Pentateuchal scroll ever found in a Torah ark. The method worked. But when Seals turned to the Herculaneum scrolls, he hit the wall that had stopped everyone else. The Engedi scroll used metal-based ink containing iron or lead. Metal shows up clearly in CT scans because it has higher density than parchment. The Herculaneum scrolls used carbon-based ink. Carbon ink has nearly identical density to carbonized papyrus. In CT scans, it was invisible. No contrast, no visible text. Seals had an idea. Maybe machine learning could detect subtle patterns that human eyes could not see. Maybe there were microscopic texture differences or tiny density variations that algorithms could find. But proving this hypothesis would require massive computational effort, more than his small academic team could accomplish. In 2022, a Silicon Valley entrepreneur named Nat Friedman discovered Seals' work through an online lecture. Friedman was the former chief executive officer of GitHub. He understood how open-source collaboration and financial incentives could mobilize global talent to solve hard problems. He proposed transforming the research into an open competition. In March 2023, the Vesuvius Challenge launched. Seals released his software and CT scan data publicly. High-resolution 3-dimensional X-ray images of 2 intact scrolls and several fragments were included. The challenge offered $700,000 to the first team that could read 4 passages of at least 140 characters each from inside a sealed scroll. Smaller prizes were offered for incremental achievements along the way. 2,763 competitors and teams from around the world joined the effort. They included students from China, archaeologists from Ukraine, medical imaging researchers from Germany, machine learning engineers from Japan and South Korea, and computer scientists from the United States and Europe. They had until December 31st, 2023. The fragments. Here's what made progress possible. Over the centuries, pieces had broken off from scrolls during earlier unrolling attempts. These fragments existed with both CT scans and visible text that had been photographed under infrared light. The fragments provided ground truth. Researchers could train machine learning models by showing them CT data and the corresponding visible text. The models learned to predict where ink was present based on patterns in the X-ray images. A parallel competition on a data science platform called Kaggle focused specifically on ink detection in fragment data. Teams developed increasingly sophisticated models. The top models showed promise, but they did not immediately transfer to intact scrolls. The breakthrough. In August 2023, a 21-year-old undergraduate at the University of Nebraska named Luke Ferrator made a discovery. He had been applying modified machine learning approaches to virtually unwrapped scroll segments. On a Saturday night in late August, he was at a party in Omaha when he received a message from a collaborator. New processed images had been uploaded. Ferrator examined them on his phone, and he saw something no one had seen in nearly 2,000 years: letters, Greek letters, emerging from the darkness. In October 2023, Ferrator won the $40,000 First Letters Prize. He had identified the first legible word from inside a sealed Herculaneum scroll. The word was porphyros, Greek for purple. A key insight emerged during this period. The ink showed a distinctive crackle pattern, like peeling paint or dried mud. This texture difference was invisible to human eyes examining CT scans, but machine learning could detect it and amplify the signal. Between November and December, 3 researchers who had made individual breakthroughs joined forces. Luc Ferrator from the United States, Youssef Nader, a doctoral student at a Berlin university originally from Egypt, Julian Schilliger from Switzerland, who had recently earned a master's degree in robotics. They combined their techniques, Ferrator's ink detection innovations, Nader's domain adaptation methods, Schilliger's segmentation software, which he called Thaumato Anacalyptor. On December 31, 2023, they submitted their results. What they found. The team had been required to read 4 passages of 140 characters each. They far exceeded requirements. Over 2,000 characters, 15 complete columns of text, approximately 5% of the scroll. Papyrologists identified the text as almost certainly written by Philodemus of Gadara, an Epicurean philosopher who lived from approximately 110 BCE to 35 BCE. He was the personal philosopher of the villa's likely owner. At least 44 of his texts had previously been identified in the collection. But this text was new, previously unknown, a philosophical work that had been completely lost to history. The subject was the nature of pleasure, a central concern of Epicurean philosophy. One translated passage reads, "We do not right away believe things that are scarce to be absolutely more pleasant than those which are abundant." The author contemplates how abundance or scarcity affects our experience of pleasure. He examines sources of enjoyment like music and food. He criticizes unnamed philosophical opponents, likely Stoics, for having nothing to say about pleasure when it is a question of definition. This aligns with core Epicurean teaching. Contrary to popular misconception, Epicureanism was not about indulgence. It was about achieving peace through modest living, friendship, and freedom from irrational fears. Pleasure meant the absence of pain, not hedonistic excess. After 2,000 years, scholars could read new words by an ancient philosopher discussing questions that remain relevant today. What makes experiences pleasurable? How does availability affect our enjoyment? What is the relationship between abundance and satisfaction? How the technology works. The complete process involves multiple sophisticated steps. First, high-resolution computed tomography scanning. The scrolls are scanned using X-ray computed tomography at resolutions of 7 to 10 micrometers per voxel. That is a 3-dimensional pixel, smaller than a human hair. Modern synchrotron facilities can scan a large scroll in under 2 hours. Second, segmentation. The rolled papyrus must be traced through the 3-dimensional volume. This is extraordinarily difficult because papyrus layers are extremely thin and may be fused, torn, or distorted. Machine learning algorithms identify likely papyrus surfaces, and geometric processing constructs continuous surfaces through the scroll. Third, flattening. Once a surface is traced, it is computationally unrolled into a 2-dimensional image. The curved 3-dimensional surface is mapped to a flat plane, and texture information from the computed tomography data is transferred. Fourth, ink detection. This is where AI makes the critical difference. To human eyes, the flattened images show nothing. Carbon ink on carbonized papyrus, no visible text. But machine learning models trained on fragments with known text learn to detect subtle patterns, microscopic texture differences, slight density variations, surface irregularities invisible to human observation. The models do not use optical character recognition or Greek language models. They detect ink purely from the physical properties in the computed tomography data. It is a remarkable demonstration that the signal exists, even though humans cannot perceive it directly. What remains? The February 2024 announcement was just the beginning. In February 2025, researchers announced a successful virtual unwrapping of another scroll from Oxford's Bodleian Library. It was scanned at the Diamond Light Source synchrotron in the United Kingdom. It contains more recoverable text than any previously scanned scroll. The first word translated was diatrope, Greek for disgust. But significant challenges remain. The ink detection methods that worked on the first scrolls do not generalize to all scrolls. Researchers discovered that some ancient inks may have contained trace metals that enhance detectability. Others may require different approaches. Current readable coverage is approximately 5% of one scroll. The goal of reading 90% has not been achieved. A $200,000 prize for that milestone went unclaimed. Segmentation remains labor-intensive. Tracing papyrus surfaces through damaged, distorted scroll structures requires extensive computational work. What might be found? Between 600 and 800 unopened scrolls exist in museum collections. Based on the library's known character, most will likely contain more works by Philodemus and other Epicurean texts. But scholars dream of bigger discoveries. Lost works of Greek tragedy and comedy. Historical accounts now known only from later summaries. Scientific or mathematical treatises. Personal correspondence from the Roman elite. And there is an even more tantalizing possibility. Entire levels of the Villa of the Papyri have never been excavated. Roman villas of this grandeur typically contained two libraries, a Greek library for philosophy and literature, and a Latin library for Roman works and legal texts. The discovered scrolls are overwhelmingly Greek. This has led scholars to hypothesize that only the Greek section was found. A Latin library may exist in unexcavated portions of the villa. If it exists, it might contain lost Roman classics, early editions of Virgil's Aeneid, historical documents from the late Republic, and works mentioned by ancient authors but never found. Richard Janko suggests the villa was a museum-like place to show off spectacular works of art and literature. If so, we might even hope for an early edition of the Aeneid. Philodemus knew Virgil personally, the human story. The three winners were young researchers who had never met in person. Luke Ferrator was a 21-year-old undergraduate with no prior classical training. He discovered the first letters while checking his phone at a house party. Yusef Nader was a doctoral student in Berlin who developed crucial domain adaptation techniques. Julian Schilliger had just earned his master's degree in robotics. His segmentation software improved sheet extraction by a factor of 10,000. They lived on different continents. They collaborated virtually in the final weeks of the competition. They combined complementary skills to achieve something no one had done in 2,000 years. And then there is Brent Seals. He began working on virtual unwrapping in 1995. For nearly 30 years, he developed and refined techniques. He published research, he faced skepticism, he persisted through setbacks. When the grand prize was awarded, Seals said he had always predicted near certainty of success. The scientific basis for his expectations was clear before they initiated the contest. 30 years of persistence, finally vindicated.